definition holds precisely the same as it did in the real case, except that an epsilon neighborhood of L is an interval in the real case, and it's a circle, a disk. I shouldn't say a circle. Remember, the circle is the thing we call the circumference. The disk is the inside of the circle. The neighborhood is a disk in the complex case. Namely, notice that to say that the absolute value of a sub n minus L is less than epsilon still means that a sub n is with an epsilon of L. The difference is that the domain of L is now the xy plane, the Argand diagram. So to be with an epsilon of L, I now take a circle centered at L with radius epsilon and draw that circle. And what I'm saying is that if the limit of the sequence is L, after a certain number of terms, all the remaining terms are inside this circle. In other words, just as in the real case, in the complex case, the limit replaces an infinite number of points, numbers, you see, an infinite number of points by a finite number plus one dot. In other words, there's a bunch of numbers that may lie outside the circle, but after a point, after a certain term, all of the remaining terms lie inside this particular disk. And structurally, you see, that's exactly the same thing that happened in the real case. Consequently, since the structural definition is the same, since the geometric interpretation is the same, except that disks have replaced intervals, I would expect that all the limit theorems held, just as in the real case, and indeed they do, and we'll talk about those in the exercises. In a similar way, though, that we went from sequences to series in the real case, we can now do the same thing in the complex case, namely, suppose C1, C2, C3, etc. represent a sequence of complex numbers. By the infinite sum, n goes from 1 to infinity C sub n, I simply mean the limit as n goes to infinity C1 plus etc. Cn, noticing that this is what? One number, it depends on n, and it's what you call the nth partial sum of the series, that we've added up C1 through Cn. The next term would be obtained by adding on Cn, C sub n plus 1, etc. But notice again the similar structure, and consequently the usual theorems for series that apply to the real variable case apply to the complex variable case. Again, what's the only difference? The only difference will be that intervals of convergence will be replaced by disks or circles of convergence.